Here are some big headlines from the world of the very small. This is the year that quantum computers leap out of the lab. Quantum computing breakthrough could change life completely. Quantum physics is invading biology. Now, it's not a leap to say that the quantum era has been proclaimed, or at least that the term quantum is flying around like a greased photon, but it may not be clear what that means for our everyday lives. I mean, what has the wave-particle duality ever done for me personally? And what will it do? I'm Seth Shostak, or maybe I'm not.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology, and in this episode, the tech industry has proclaimed that your laptop will soon go the way of VCRs and floppies. Instead of bits, your next computer will use qubits, process at stunningly faster speeds, and possibly solve the most intractable scientific problems. Find out what it means to be at the dawn of the quantum computing age, the weird case for the universe itself being a quantum computer, and how a new field of study for the living world, quantum biology, may even revise our definition of life. It's weird stuff. It's quantum, why we want 'em.
As if technology wasn't already moving fast enough.
How can I help you?
I have a question about my smartphone.
Which model?
The XCR 270.
Oh, sorry, but we don't carry that anymore.
But I bought it here, this morning.
I know. Listen, we're going to trade it in for the XCR 275. They released it at noon today. It's awesome with more RAM and 2 headphone jacks. Here.
Thanks, I'll take it.
Wait, hang on. I've just learned that the XCR 275 is now discontinued. I'm going to need that back.
What?
So I can swap it for this, the XCR 275 Plus, released 10 minutes ago.
Okay, but...
Don't worry, it still has 2 headphone jacks.
Now, computers may be ready to take their biggest leap since the invention of the mouse.
The tech industry has declared this the year of quantum computing. They're priming our subconscious with subatomic promise, lauding the efficiency and speed of quantum over classical, and suggesting we will get more computing certainty from uncertainty.
Quantum, 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 it's everywhere. It's our latest catchphrase.
Hey, it's up.
It's quantum.
That's cool.
We may have absorbed the concept and nomenclature, but as far as the actual physics of quantum mechanics goes, well, even Nobel Prize-winning physicists can only shrug.
Quantum mechanics is weird. It's strange and funky, counterintuitive. Niels Bohr once said, anybody who can contemplate quantum mechanics without getting dizzy hasn't properly understood it.
Later, MIT physicist Seth Lloyd argues that the universe itself is a quantum computer.
Which goes to show that quantum physics may be weird, but it's not dull, although that's not to say that descriptions of modern physics don't prompt glassy-eyed faces and the sound of sawing wood.
And when Paul Dirac was teaching a course at the University of Cambridge, students wanted to learn from the horse's mouth what quantum mechanics was all about. And Professor Dirac simply started with this: consider an infinite dimensional Hilbert space. And from there, it was all downhill.
We can try to do better than that with physicist Michael Raymer.
We once thought we knew everything we needed to know. Back around the time the slide rule was invented and the Puritans were blown off course and landing at Plymouth, Isaac Newton figured out his physics. And for a couple of hundred years, that seemed to be the end of the story. It described everything in nature that depended on physics, which is to say, just about everything in nature.
The theory of Newton, which is classical physics, describes particles in terms of a path or trajectory, such as the Earth traveling around the sun. That would be considered a path. But when you get down to the scale of single electrons in an atom, it's no longer possible or appropriate to talk about a path.
Now, we know that everything is ultimately described by quantum mechanics, but you don't have to use it all the time. If you're describing the motion of an elementary particle, such as an electron, well, then using Newton's physics just won't do. But for a larger object, such as a baseball, it's better to use Newton's laws to describe how the baseball moves through space.
If a pitcher throws a baseball to the catcher, then we know that we can observe that baseball traveling through space. It follows a certain path, maybe a straight path or maybe a curved or arched path. And then when it hits the catcher's mitt, you hear a sound. Now, if that same experiment occurs in a completely dark room, we know the pitcher throws the ball, and we know from this that the catcher received the ball, then we know that that ball took a certain particular path through space. On the other hand, if you do the same experiment with an electron, And it starts at one location in a very dark room, so you cannot see where it's going at all times. And then you hear it arrive at a detector, and it goes click. Then you know the electron arrived at the detector. But the big difference between the electron and the baseball examples is that you can never ascribe a particular single path that the electron took from its starting point to its final destination. In fact, there are an infinite number of different paths that you have to account for. And in some sense, the electron moves through space by sampling all of these infinite number of paths continuously until it finally arrives at the place where it's detected.
That idea of sampling an infinite number of paths is something to remember when we discuss the advantages of quantum computing. Michael Raymer is author of Quantum Physics, What Everyone Needs to Know.
So, Michael, there's all this weird behavior at the quantum scale. And can you introduce us to some of the particles that we would meet if we could shrink ourselves down to and climb around inside an atom?
Inside of an atom, the only really important constituents are the electron, the proton, and the neutron. The proton and neutron are confined into the nucleus, a very small region at the center of the atom, and the electron moves in some way around the nucleus. We don't have to concern ourselves with particles such as quarks or Higgs bosons, because those particles really have to do with high energy phenomena, which don't really apply to atomic physics and chemistry and molecular physics.
Now, are there times when you're thinking about quantum physics where even you, someone who lectures on this, feels like you don't really understand it and it's sort of just, you have to take it on faith, if you will?
Well, it's dangerous to say we don't understand it. It's certainly true that we don't know why the universe is the way it is, but physics has never claimed to know that. Physics is really an exercise of building models that describe how the universe behaves. And quantum mechanics is by far the most precise and accurate model we have that can describe the behavior of atoms, molecules, and high-energy particles like quarks and the Higgs boson.
But you, when you're thinking about the quantum scale, are you ever befuddled by the physics?
Yes, if I try to describe the behavior of single electrons traveling through some region of space, and I try to explain to a layperson that the electron doesn't follow a particular trajectory, and I can't say that it follows both trajectories or two different paths, and I can't say that it follows neither path nor trajectory, then usually people look at me with a puzzled look. And they say, how is that possible? Or what does that mean? And the answer is, I can't say from a common sense, everyday language point of view why that is and exactly what it means.
Now, is quantum physics compatible with classical physics or classical Newtonian physics?
Yes, quantum physics has to be compatible with classical physics because any object, such as a baseball, is made up of an enormous number of protons, neutrons, and electrons, each of which obeys the principles of quantum mechanics. Yet the baseball, as an overall object, it obeys classical Newtonian physics very well. So it's really, in some sense, a matter of scale. And for larger objects, we can typically use the classical theory perfectly well. But for very small objects, we usually have to resort to the quantum description.
And where is that demarcation once you get below what size?
There is no clear demarcation. It really has to do with the particular scenario or experiment that you're performing on the object. And people now are attempting to even demonstrate quantum-like behavior of pretty large objects, such as a single virus, which has been somehow launched through a vacuum chamber that contains no air, and one is trying to monitor the location of this large complex particle. If you do this particle with exquisite care and precision, you might actually be able to see cases where the classical theory fails to describe the motion of that large object correctly.
Now, there is some weird behavior that happens on this scale, right? Now, is it true that an electron can be in two places at once?
That's not really correct to say it that way.
Okay,
and
but it's fair enough. It's fair enough that I have that idea, right? That's what I've heard.
It's fair enough, but it's a misuse of language. And it's an important point because the whole distinction between quantum physics and classical physics is the very fact that when you're talking about a single elementary particle like an electron, the concept of position or location is not actually a valid concept. So it's not correct to say the electron is in two places at once, nor is it correct to say that it's in neither place. It's really that question has no answer until you make an observation and you look and you see where it is. And now when you do that observation, you look, you see, oh, it's only in one place.
What is quantum entanglement?
Quantum entanglement is a description of two particles that are both being described quantum mechanically. An example would be if I have two electrons, and each electron could be in one of two different boxes. Now I ask, okay, which electron is where? And again, you can't really say that's a meaningful question until you open the box. However, you can ask the question, in which box will I find the electron most likely if I open the box? Now, if there are two electrons, the answer to that question for the second electron depends on what the first electron is doing. And so this is called the entanglement between the states of these two electrons.
It's really pretty freaky.
It is.
Well, can we see quantum effects in our daily life?
You can't see them directly, or at least you wouldn't perceive them as quantum mechanical effects. However, every time you look at a LED, a light-emitting diode, it's emitting light in a way that has to be described correctly using quantum mechanics. In fact, the Nobel Prize was recently given for the invention of the blue light-emitting diode. And that's because it required a great amount of insight into how electrons and photons interact quantum mechanically in order to design and build those LEDs.
So the properties of quantum physics that we already rely on for everyday objects, including, I might add, cell phones and GPS, are now being applied to a new generation of computers that he says would operate differently than the classical variety, which is the one you used earlier to download that banana bread recipe.
In an ordinary computer, one switch will affect its neighboring switch. So if the first switch is on, it may cause the second switch to be on. The on-off nature of these switches is called binary, and you can call those zeros and ones, but I'll call them on and off.
A pioneer of quantum computing, MIT physicist Seth Lloyd says each 0 or 1 is a bit of information. It's a way of coding information, such as the amount of charge on a capacitor, a device for storing electrons.
Like 0 is, whole bunch of electrons over here, capacitor uncharged. 1 is a whole bunch of electrons over there, capacitor charged up.
And in an ordinary computer, there are millions of these switches all arranged in a certain way, and there's a cascade of one switch affecting its neighbor and then that one affecting its neighbor, etc. And this leads just like to a large calculation, almost like a mechanical calculator. But at no time in those ordinary computers is there quantum entanglement.
In a quantum computer, say you're storing a bit on a single electron, you can have, electron over here, that's 0, electron over there, that's 1. But because of the funky nature of quantum mechanics, you can have electron here and there at the same time. That can't be done classically, but if you can do that in a quantum computer, then you can do computations in a way no classical computer could.
Next, we'll find out just what kind of computations a quantum computer can do when classical bits are replaced by qubits. Also, Seth Lloyd on why the universe is a quantum computer. Many thanks to Michael Raymer for sharing with us the big ideas in the world of the very small. He's a physicist at the University of Oregon and the author of Quantum Physics, What Everyone Needs to Know.
It's Quantum, Why We Want 'Em on Big Picture Science. Physicist and mechanical engineer Seth Lloyd is a pioneer of quantum computing. In his lab at MIT in Cambridge, Massachusetts, he designed one of the first practical quantum computers.
In his early 20s at Cambridge University in the UK, he came up with an explanation for why particles become entangled. He presented it as part of his doctoral thesis in 1988 and then heard not thunderous applause, but crickets.
Quantum information theory was not popular at the time, says Dr. Lloyd, and he admits he came darn close to driving a taxi cab.
Taxi!
Where to?
Cafe on the River Cam.
Well, here's the thing.
That cafe was on the right bank of the river this morning, but a spontaneous spin flip has altered the wave function, and while there's a 28% chance it is where it was, Heisenberg's uncertainty principle suggests we won't know until we get there.
You know, it's such a beautiful day. I think I'm going to walk.
And as much as we'd love to have the experience of taking a metaphysical taxi to lunch, we're glad that Dr. Lloyd maintained his interest in quantum theory, eventually developing an experiment in quantum teleportation. He joins us to explain how quantum computing, qubits rather than regular bits, will change everything.
Seth, we're hearing a lot about the advent of quantum computing, but since quantum mechanics is so strange, so counter to our intuition, do we really grasp it well enough to build computers?
Good question. Well, quantum mechanics is weird. It's strange and funky, counterintuitive. Niels Bohr once said, anybody who can contemplate quantum mechanics without getting dizzy hasn't properly understood it. So you're right. It's weird. And it is true that quantum mechanics says that at very microscopic levels, there's all kinds of extra noise and chancy behavior going on, which could interfere with getting a computer to do something that you want it to do. But this quantum weirdness also opens up all kinds of opportunities for doing computation in ways that no classical computer could ever do. That is, it's not a quantum bug, it's a quantum opportunity.
Okay, it's a quantum opportunity. So does it allow you to do things faster, or does it allow you to do more things, or maybe both?
Well, so quantum computers, the devices that store information at the level of, individual atoms, photons, elementary particles, or funky quantized superconducting circuits, and then it processes that information using the laws of quantum mechanics. Now, the size of the bits in a quantum computer can be very, very tiny, but that doesn't make the quantum computers physically faster. That is, they don't necessarily flip those bits faster than our classical computers. But what it does mean is that they can use funky effects like quantum entanglement to solve problems no classical computer ever could.
So perhaps I could liken a quantum computer to having, a gazillion laptops. Instead of the ones and zeros in this part of the circuitry over here, I've got everything in between. So each one of these gazillion laptops is running a slightly different program?
It is like that, but not exactly like that. So indeed, a quantum computer, if you have a single quantum computer and you give it an instruction, let's say 0 says add 2 plus 2, and 1 instructs it to add 3 plus 1. Now you give it a quantum bit, a qubit, that's 0 and 1 at the same time. Now this single computer, one computer, is both adding 2 plus 2 and adding 3 plus 1 at the same time in something called quantum parallel. So our ordinary classical minds have a very hard time grokking this. So it's one computer that's doing two things at once. And you can easily get one computer to do 4 things at once, or 8 things at once, or a gajillion things at once. Or even, with 300 qubits, you can make it do 2 to the 300 things at once, and 2 to the 300 happens to be the number of elementary particles in the universe.
My gosh, that sounds like the last computer I'd ever have to buy.
Yeah, I don't know about that. I don't know if they're not ready to really run Microsoft Word on them.
Well, now, aside from such trivial matters as how do you build a quantum computer and, and how do you program it, my question would be, how do you know what the right answer to a problem is when you're getting, 2 to the 300th answers? So
one of the main differences, if you have one computer that's doing, 2 to the 300 things at once, it's not the same as having 2 to the 300 computers that are doing all those things at once. Mind you, since you'd have 2 to the 300 computers, every single particle in the universe would have to be a computer. So and you're not going to get that classically. Basically, if it's doing all these things at once, and you ask it during the process, what's it doing, it will just say, I'm doing one of these things, but it's just a random choice between all these different possibilities. So let's say it's just adding 2 plus 2 and 3 plus 1 at the same time, and you look at it and say, what are you doing? It will say, I'm adding 3 plus 1. So that's not very useful, because that's just the same thing as taking a classical computer and giving it a random program. But the secret to quantum computing, and where the fancy pants quantum stuff comes in, is at the end of the computation, you recombine all these different possibilities that are there simultaneously, and you recombine them in a way that gives you the answer to a hard problem.
So, Seth, let's say we get these quantum computers and the price comes down from $15 million. We start using them. How would our lives change? Can you give me a sense of what would be different? I mean, would I print my boarding passes faster? What?
Probably not. So if it were the case that having a quantum computer was like having, 2 to the 300 classical computers, then you'd be in great shape. You could do all these things in parallel and life would be good. But because to get the advantage, you have to recombine the different quantum waves corresponding to the different computations in a way to get the answer, there's not that many problems that you can do faster. So the most famous one is called factoring. If I have a large number, which is the product of two smaller prime numbers, like, a small example of this would be 15 is the product of 3 times 5. If you have this large number, then you can find the smaller prime numbers, and this would allow you to break all the public key cryptosystems that we use to send information privately over the internet. So if we had one of those, it would be quite disruptive. It's not surprising that agencies with 3 letters in their names are funding quantum computing research.
Yeah. Well, I was going to ask you, it sounds like something the NSA is going to want to buy.
Well, yes, actually, the NSA, they're very upfront of it from the very beginning. They actually said in a public venue that because their primary job is to protect the secrets of the country, they would prefer that quantum computers not be possible. But because their secondary job is to find other people's secrets, if they can be possible, then they want the first one.
Can I ask your opinion? Are they possible?
Oh, absolutely. I mean, I don't know about quantum computers that will break these codes, but right now, the progress now is that we have quantum computers which have, 20 or 30 quantum bits and can do, a few hundred operations. And then over the next 5 years or so, we'll have, 50 to 100. They can do thousands of operations, and then hundreds or thousands of quantum bits and can do tens of thousands to millions of operations. At that point, these 3-letter agencies would have to worry.
It sounds like we were born a little bit too soon. Well, can you give me an important problem aside from, cryptography? I mean, a really important problem that we could solve today if we had good quantum computers.
Yeah, so I'll give you 2 problems. One has been known for a long time. This was suggested by the Nobel laureate Richard Feynman in 1982, though he confessed in his talk when he talked about it that he had no idea how to do this. And in 1994, I showed how you could do this with a quantum computer, the kind we were building then and building now. It's to actually understand how other quantum systems behave. Now, quantum mechanics is strange and counterintuitive. Turns out to be strange and counterintuitive for classical computers as well. So it's very hard to understand how they behave. But if you had a quantum computer, because a quantum computer is itself doing things in a funky and counterintuitive fashion, you can simulate other quantum systems and find out how they behave. That's an application that's dear to my heart, since I've spent my life trying to make sense of how funky quantum systems behave. But a more practical application that people run into all the time would be, for example, machine learning. It's no secret that places like Google and Amazon and Microsoft are spying on us. They're collecting our data and they are processing it using complicated machine learning algorithms to figure out our personal behavioral patterns and to try to sell us more stuff. And machine learning is everywhere. I mean, it's in voice recognition software, it's in self-driving cars, it's in robotics, it's actually in, airline ticket systems. And it turns out that many of the basic methods of machine learning could be performed much more faster and more efficiently on a quantum computer. So quantum machine learning could be done actually with the kind of quantum computers that are going to show up in the next 5 to 10 years, and that might indeed make a difference.
There's been an idea floating around for decades now, namely that the universe itself could be a quantum computer. Is that just bandying jargon around to impress the innocent? Is there something to that?
Am I supposed to take that as an idea that, since I'm the person responsible for that idea, am I allowed to take well, I don't take umbrage. So I'll just say, no, it's not just bandying jargon around to impress the innocent. It's not a metaphor. I mean, you could take it as a metaphor if you want, that the universe is like a quantum computer. But in fact, it's true in a very technical sense. So what is a computer? It's something that can process information in a certain way. It can flip bits in a certain fashion and can solve certain problems. What is a quantum computer? It's a system that can flip quantum bits in a certain systematic way and solve certain problems. But the universe technically is a quantum computer because, at bottom, the universe is constructed out of quantum bits, and these bits are flipping in particular ways that allows it to solve quantum computational problems. So from the kind of mathematical, technical, and physical standpoint, the universe is a quantum computer. So it's not actually just jargon. I mean, it's just a fact. If you'd like to refer to it as jargon or a metaphor, you can, but it is a physical and mathematical fact.
Well, if the universe is really a quantum computer, does that mean there are multiple instances of everything in it? I mean, is there another one of me somewhere in a different quantum state that's, having a better day?
Oh, yeah, that is the case, I'm afraid to say. So the current picture of the universe is that the universe is spatially infinite, and that if we look at our universe, the part that we can see around us, there are an infinite number of copies out there of our universe. And there are, in fact, copies that differ only in the fact that you are having a good day in that other universe and not in this one. Or in another universe, I have my hair. Sadly, we inhabit our universe.
This sounds, perhaps this is really a bad analogy, but it sounds similar to the idea promoted by the Oxford philosopher Nick Bostrom that we might be living in a computer simulation, that this isn't real here, that our lives aren't real. It's kind of like The Matrix, the film.
Yeah, so Bostrom's idea is that we live in some alien computer that's simulating human beings. And of course, we can't disprove that as long as the aliens don't make a mistake. Though I must say that it seems a bit anthropocentric, like why would the aliens be interested in us, However, the same physics that describes how quantum computation takes place shows that if we actually demand we have a physical system that obeys the laws of physics that is simulating our universe, then the smallest system that could simulate our universe is in fact the universe itself. So if you ask this putative computer that's simulating us obey the laws of physics and simulate everything down to the last detail, then that computer is the universe.
So what you're saying is that if this idea were to be correct, it can't be simulating everything. It can just maybe simulating everything going on Earth or maybe in our solar system, but it's not doing a very good job with all those planets in, the Andromeda galaxy or something.
Exactly, you're exactly right. So it is very much like the Matrix, in which the aliens simulate only what human beings are supposedly perceiving. Again, I personally think that this fails what I call the Monty Python test. The Monty Python test is you come up with an idea and you say, how silly is this? And if it's too silly, as like in many Monty Python sketches, then you shouldn't take it too seriously. And anyway, I think this Bostrom idea is frankly too silly.
Okay, all right. So you haven't modified, then Seth, you haven't modified your lifestyle to account for the fact that maybe there's no reality to it and you can just do whatever you want.
No. I think I get up, I eat breakfast, I exercise, and I go to work. I'm satisfied with that.
Seth Lloyd, thanks so very much for speaking with us.
Thank you very much, Seth. It's been a pleasure.
Seth Lloyd is a professor of mechanical engineering and physics at MIT.
Well, the idea that the whole universe might be a quantum computer is certainly intriguing, interesting, but I got to say, I'm never going to be able to fit that computer under the seat in front of me on the airplane. But, the idea of quantum computers, now, that really is a very promising idea because, today, if you buy a high-end computer, it usually has multiple processors in it. It isn't just sort of one computer. There might be 8 in there. They're all kind of working together, speeding things up. But if you have a quantum computer, well, that might be like having, 10,000 processors in there. And so, you can take on the really big problems.
Well, what are some of the other really big problems that a quantum computer can take on? We heard that it could break some of the big codes when it comes to encryption, but what else?
Well, as Seth Lloyd said, it can't do everything that conventional computers can do. But the things it can do, it does them so much faster that it becomes interesting. For example...
Except word processing. You said it can't do that yet.
Well, I bet it could do word processing. The only thing is, you're going to write all your novels at once. I mean, I don't know how it would help. Yeah, well, I guess as long as you got the bestseller out of all those millions of novels that you wrote. But okay, decryption, sure. All right, so machine learning problems where you have a huge amount of data that you're pawing through, those benefit from this kind of computation. For example, suppose you take all the data that the CDC has about various diseases, right? And you correlate those diseases with all sorts of things. You're people over here who eat too much broccoli, and there are people there who never eat broccoli, whatever. And, for an ordinary computer to go through all that and try and find some sort of link between behavior and disease, it's not very possible. With a quantum computer, it would be.
Does quantum computing intersect with the field of big data?
Well, yeah, in the sense that you could use the quantum computer to paw through big data and, much faster and look for more things. Quantum simulations, the guys who work on quantum computers say quantum simulations, which is to say you use quantum mechanics to simulate quantum mechanics.
Whoa.
That may
blowing
sound
my mind.
Yeah, sound a little weird, but indeed, quantum mechanics, if you can solve some quantum mechanical problems, you learn a lot, certainly in physics, that kind of thing. But there are things like simulating some biological processes. You can't necessarily do that with a standard computer now because it'll take you too long.
Can you say more about how quantum computers rely on the strange behavior that we find in quantum physics in order to do this?
Yes, it's fundamentally because at the quantum level, nature is a little bit, if you will, fuzzy. Now, this explanation may be a little bit fuzzy, but you remember when Dr. Raymer was talking about how if you take something that's macro-sized, like a baseball, and you throw it, right, and you know where it went, you can follow the path of it. But if you throw an electron, well, you don't know where it went, all right? So you can imagine that if you're interested in a particular pitcher, and this guy can throw good curveballs, and he can throw good spitballs, and he can throw whatever fastballs, whatever the pitchers throw, and you wanted to make an inventory of all that, that'd be a big job, a lot of data, because he has a lot of pitches. But if you were an electron pitcher, you see, now you could use quantum computing, and you get all the pitches at once, if you will, because he's not throwing just one pitch. He's throwing them all kind of simultaneously.
But the computer is coming up with one answer. It's not coming up with infinite answers.
Good point. And that's to me the tricky part of all this. Sure, it's doing a gazillion computations at once, but I'm only interested in one answer, or at least I can only be interested in one answer at a time. And you have to shape the computer the way you ask the computer questions so that it gives you the answer that you want out of all those computations. And that to me is kind of tricky, but that's what they say they can do.
Well, while quantum physics may deliver us the next generation of computers to take on the really big problems, could it also deliver us answers about the fundamentals of biology, how birds may use quantum physics to navigate, and other tales from the new field of quantum biology next?
It's Quantum, Why We Want 'Em on Big Picture Science. Quantum physics is weird. The idea that the universe is a quantum computer, it's beyond weird, it's bizarre. But we may have to adjust to the fact that spooky behavior, as Einstein called quantum mechanics, surrounds us, maybe even closer than that. It may be responsible for the basic workings of life itself.
From how plants photosynthesize to how birds navigate, the new field of quantum biology claims to have discovered strong evidence that life itself depends on quantum mechanics.
Scientists working in the field of quantum biology say they may be on the verge of explaining what keeps us alive, says Joe Mcfadden, a biological scientist at the University of Surrey in the UK. This is a truly new idea because most scientists have believed that all you really needed to understand life was to understand chemistry, molecules, nucleotides, amino acids. And yeah, sure, organic chemistry, it's incredibly messy and it's hard, but at least you didn't have to get down to the quantum level. But that may be about to change.
While it's true that most aspects of existence can be described by Newtonian mechanics, our heart beating, our run through the park, life now seems to be rooted in the quantum realm. Life on the Edge is Dr. Mcfadden's book about the growing field of quantum biology.
Up until fairly recently, it was a speculative thought experiment. Many of the quantum pioneers, for instance, Erwin Schrödinger of the famous Schrödinger's cat, did propose back in the 1940s that life depended on these weird aspects of quantum mechanics. But that was just a speculative proposal, and it has remained that way up until about a decade or so ago, when scientists really developed technology to look at how individual molecules are behaving inside living cells. And this technology has only been available fairly recently. And when scientists have used this technology to probe what goes on, for example, inside a leaf or inside our own cells that have enzymes that work to make all the biomolecules in our cell, they find that they're doing this weird quantum stuff, the kind of quantum stuff that electrons do, photons do, but we thought wasn't really relevant to big stuff like people or trees. And what is really remarkable about this field of quantum biology is that to a certain extent we're kind of seeing this weird quantum mechanics, the stuff that's usually hidden from sight, it's actually helping to keep us alive.
Well, why don't we go to an example? I believe you've written that a robin's instinct to fly south, for example, might involve quantum physics. Now, I think everyone has assumed for a long time that birds are able to navigate by sensing somehow the magnetic field of the Earth. But, that doesn't, I have a compass and I don't know, I never think of it in quantum mechanical terms, although perhaps it does work that way. How does a bird sense the magnetic field of the Earth with quantum mechanics?
Yeah, this is indeed a very exciting and interesting and fascinating field that, as you say, the Boy Scout's compass doesn't need quantum mechanics to explain how it works. It just points at north and south. But what was discovered about the bird's compass is it didn't seem to behave like a Boy Scout's compass. For example, it needed light. It didn't work in the dark. It needed the bird's eyes to work. And it also didn't distinguish between north and south. It would just kind of point at the nearest pole, whether it was the North Pole or the South Pole. So if you took a bird that was used to navigating in the North Pole into the Southern Hemisphere, it would go in all the wrong directions. So there was something very odd about the bird's sense of navigation, its magnetic compass. And a scientist called Thurston Ritz, an American scientist, in fact, came up with the idea that, well, this could be accounted for if it involved this peculiar property called quantum entanglement. And this is something so weird that even Einstein couldn't believe it. And remember, Einstein gave us black holes and bending space-time, but he said, no, quantum entanglement, that's too weird. But what it allows particles to do is to, when they're separated, they actually still can kind of communicate in a weird kind of way. And the line between them, if you set up particles in a certain way, the line between those two particles is sensitive to the Earth's magnetic field. So Thurston Ritz proposed, well, maybe this is how the bird's eyes work and the bird's navigation sense works. And he teamed up with a pair of ornithologists to test the theory. And the test was that if this was the case, then the bird's compass should be disrupted by high-frequency radio waves. And they did the experiment, and indeed it was. So that doesn't actually prove that it's quantum mechanical what's going on in a bird's eye. It's obviously very difficult to study directly what's happening in a bird's eye when they're navigating around the globe. But there's no other theory out there which accounts for these observations.
But let's assume that it's true. Is that the kind of ability that could be passed to the next generation through the usual, DNA and genetics and stuff like that?
Absolutely. This is something that every bird is born with. Well, birds that have a magnetic compass, birds like the robin, birds like pigeons, homing pigeons also have a magnetic compass. This is something that's inherited. So it's something that's encoded in our DNA. And, our DNA is also has quantum aspects to it. It's a single molecule, and ask any physicist what science you need to explain what happens within a single molecule, and they'll point to quantum mechanics. So it's not too surprising when you really think about it that life depends on quantum mechanics, because it's the only thing that really manipulates, that we can see around us at least, that manipulates particles. It manipulates electrons, protons, all sorts of particles. That's what life really does. So if it's doing all this, manipulating individual particles, it's bumping into quantum mechanics, and how to manipulate those particles is being captured by evolution and stored in our DNA. So we have that information in our DNA, how to make use of these capabilities.
Now, you've given us the example of the bird's navigation. I assume there are others, but, I might argue, okay, maybe in that one case or maybe one or two other cases, quantum mechanics is decisive. Some people have suggested, for example, that if you have an idea, that your brain is doing that using quantum mechanics somehow. But, it's been said now that quantum mechanics may not just be sort of incidental to life, but actually decisive in life.
Yeah, absolutely. The recent findings about a decade ago that how energy is captured by the process of photosynthesis, which goes on inside microbes and plants and produces all the plant material on our planet, really, it depends on quantum mechanics in that the energy transport, which is usually an inefficient process, is extraordinarily efficient inside photosynthesis systems. And no one really understood why. And when scientists shone laser light at these systems and studied at a molecular level exactly what was going on, they found that the energy was being transported not the usual way where it goes down a single wire, say, from one place to another. It was traveling by multiple routes simultaneously. And that's only something that quantum mechanics can do. And it's involved in, if you look out and see a tree or grass lawn, then that's going on inside the tree and the grass. And it's responsible for making all the biomass that we eat. And that's only one aspect.
Well, it sounds like a lot of our research has been proceeding in a way on the wrong assumption. Let me ask, could quantum mechanics have some role in the origin of life? I mean, that's one of the big questions in science, how, you went from a sea of just a whole bunch of stuff to something that could reproduce accurately, is something that was alive. And we still don't know how that happened. I think that British physicist Fred Hoyle once said that the chances that this happened kind of randomly were very small. He likened it to a tornado going through a junkyard and assembling a jet aircraft or something like that. Now, could quantum mechanics sort of change the odds? Do you think it was essential to getting life started?
Yeah, I think so. This is, of course, at the very speculative end of quantum biology. But as you said, Fred Hoyle pointed out the problem of the origin of life, that it seems an extraordinarily improbable event to generate life from inorganic chemicals just coming together by accident in a very unique and novel configuration that allows them to self-replicate. No one's managed to make that happen in the laboratory yet. No one can make life from scratch. So it's still a mysterious process, how that happened 3.5 or so billion years ago on our planet. And one of the things that quantum mechanics can do, and is utilized in a new kind of generation of computers that scientists are working on called quantum computers, is you can kind of solve multiple problems simultaneously. Instead of trying one problem and then another and then another and then another, quantum mechanics allows systems to try and solve multiple problems together. So it means that things that could be very improbable in the normal classical world, as we call it, can happen in a quantum world. And it's sometimes called the quantum multiverse, where everything possible is happening at some weird quantum level. And if in that quantum multiverse there is the possibility of life, then it would happen in that quantum multiverse. So it could be that the ability of quantum mechanical systems to explore multiple things to do at the same time, one of those trillions of possibilities was life. And it was really quantum mechanics that made it possible by allowing systems to do multiple things at once.
It sounds like it might have been the original quantum computer, which is highly touted for being able to do all these parallel computations. And in a sense, that's kind of what you're suggesting for the start of life.
Yeah. As I said, it's very speculative. But yes, myself and my colleague Jim Al-Khalili have proposed this, that maybe life came out of a kind of quantum computation in the universe to generate the first life form, that it was an extraordinarily improbable event. But because quantum computers can do everything at the same time, and as many scientists have argued, such as Seth Lloyd in the US, the universe can be considered to be a kind of quantum computer, and maybe its first problem, or one of the first problems it solved, was how to make life.
Well, finally, John Joe, what do you see as the larger implications of quantum biology? Our understanding of quantum physics sort of complicated our Newtonian view of the universe, but it also gave us semiconductors, computers, even an understanding of how stars work. So there were practical offshoots. What about quantum biology? Are we going to build quantum computers that in some sense might come alive, or just what?
Yeah, I think there are enormous potential in the field of quantum biology. As you mentioned about computers, one of the features of quantum biology that made physicists stand up and say, "Way, this is strange," is that the kind of quantum stuff that they have been trying to get going in their laboratories by cooling systems down to absolute zero, performing experiments in absolute vacuums or as close as they could reach, and shielding systems from any vibrations, that's the kind of way that quantum physicists would do experiments to try to detect the kind of quantum phenomena that are going on inside your body or inside the leaf of a plant or any other animal or plant or microbe on our planet. So there's a big mystery there. How does life manage to do this kind of stuff that we've been trying so hard to do in technology to build quantum computers and other quantum devices? And we're finding it hard to do it at any reasonable kind of temperatures that we live in, but somehow our cells manage to do that. And discovering how they do that, how they manage to achieve these essentially quantum computations inside our cells, could crack the problem of quantum computation and maybe make it amenable to build quantum computers that will work on our desktops. So that's one aspect of it. But understanding how biology works at a fundamental level, understanding how enzymes work is the key to understanding how to design drugs. So if we are uncovering new mechanisms for how enzymes work, it can enable us to design new drugs perhaps. So that's another vast area. But for me, actually, I find the really interesting part is the question that has always, as a biologist, has always been the deepest question to me, is what is life? What is it about? We've never managed to synthesize life. The famous physicist Richard Feynman said, "If I can't make it, I don't understand it." And we can't make life from scratch. So is quantum biology, is the quantum mechanics inside our cells, is that the key to it? And maybe by understanding the role of quantum mechanics inside cells, maybe we'll be able to crack Richard Feynman's problem and actually make life from scratch, taking chemicals on our lab bench and turning them into a living cell. Synthetic life from the bottom up. And that, I think, would be the most extraordinary technology that we could possibly invent, maybe give us this revolutionary new technology of synthetic life.
John Joe Mcfadden, thank you so very much for speaking with us.
Thank you very much for listening to me, and thanks again, yes.
John Joe Mcfadden is a biological scientist at the University of Surrey in the UK. His book is Life on the Edge, The Coming of Age of Quantum Biology.
There's something reminiscent about the history of relativity in all this, because that was also developed about the same time, roughly 100 years ago, as quantum physics. And, for a long time, nobody really had any application for relativity except explaining some of the things in the cosmos. And today, there are all sorts of applications. Almost everything you use, it does involve a little bit of relativity. True with quantum physics as well, but I just had the feeling that the door is opening to all sorts of new things, because quantum biology, nobody ordered that. That's totally new. And I thought it was very interesting, the suggestion that the origin of life may have depended on quantum mechanics, because if you just say, hey, look, take a big ocean and let all this stuff in there just cook around as a giant primordial soup, you'll cook up life. And maybe without quantum mechanics, you'd never cook up life because it would take forever.
So the idea is, if life was cooked up the way that ideas are cooked up in a quantum computer, you would have multiple computations, and then one of them would produce life.
Right. The right answer would jump from the back of the book to the front of the book. The other thing that struck me when we were talking about quantum computers was the possibility of using them for what are called ancestor simulations. We've talked about those occasionally on this show, where, it may be that reality is not reality, and this is all just somebody's code running on a quantum computer that's being built 50 years from now, and they just want to simulate this part of history.
So we are the ancestors in that scenario.
We are, yes. You're just code, Molly, I hate to tell you.
I can feel the code coming on as you speak. Or, as John Joe Mcfadden says, we use quantum computers and our understanding of quantum biology to synthesize life. And you create synthetic life.
Yeah, that's another thing, right? Yes, Quantum Jones, here he is, synthetic life. I don't know. There are people who are trying to synthesize life today in the labs, and I don't know whether they're using quantum physics, but maybe they should be.
Well, thanks to the people who are never in one place while helping us produce the show. Senior producer Gary Niederhoff, operations manager Barbara Vance, and intern Sarah McQuaid.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including investigating habitable worlds in our solar system. And a big thanks also to our listeners.
Your ears have been attuned to Quantum, Why We Want Them. If you'd like to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org and also now on YouTube.
And if you're a podcast listener but prefer listening to over-the-air radio because who knows which path those radio quanta took to reach you, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
And if you listen to our show via iTunes, we invite you to leave a review on our iTunes page. And to reach us directly with your comments, throw in faint praise, email it all to bigpicturescience@seti.org.